All right, we're ready to get started on chirality. Before we do that, let's just quickly review what we did so far, right? So in chapter 1, we went over like basic concepts in organic chemistry. Namely, what is an atom, electron configuration point of view? What is a chemical bond? We went over several different bonding theory, including classical bonding theory, that's Lewis dot diagram, and VSEPR that tells you what the shape of your molecule looks like in three-dimensional, and also how to draw your molecule with the wedge and dash configuration, and how to read some kind of drawing using the line bound formula. And then in chapter 2, we start talking about conformations, right? So you can draw the molecule using the wedge and dash configuration. You can also look at it from the Newman projection, which tells you the eclipse versus the staggered versus the eclipse conformation. You can have rotation of the single bond that give you different conformation that have higher or lower energy. We also went over structures like cyclohexene, where you have a chair molecule like this one, and know how to draw the chair molecule, know how to rank the stability of different conformation of your cyclohexene. So that's what we did so far. And now we want to move on to a concept that's absolutely important in organic chemistry, which is chirality. Again, when we're talking about chirality, as we quickly introduced in our last lecture, we're talking about the handfulness of molecules. So this is a little bit jargon-like. What exactly is it? So when we're saying chirality, okay, yeah, one more thing, I think I forgot. Administrative. So midterm exam is next Wednesday. Lots of you has been emailing me about like coverage and details and everything. So I will post an announcement on BrainLearn this Friday. So in that announcement, you'll find out information including what are the topics being covered on midterm exam 1, which basically is everything from lecture 1 to this Friday. I don't know that yet, so I can't tell you what will be on the exam. And then in that announcement, I'll also give you information regarding like what you can bring to our exam, what you cannot bring to our exam, what the format of our exam be, namely like how many multiple choice are there, like how many short answer problems are there, etc. All right, and also like when and where the exam is gonna take place. So stay tuned until Friday for anything regarding the midterm exam. Next Monday, we'll have a buffer lecture. So that buffer lecture is basically something I use to catch up things that we discussed and also to clarify concepts that people think are confusing and make sure you know what my expectation for you is. All right, so that's for midterm exam. The other thing is I'm moving my office hour tomorrow to Thursday. I have a doctor's appointment. I can't be here tomorrow, but I'll be here on Thursday. So the same time, outside my office, I also reserve some like small conference room for you to use. So office hour moved, and stay tuned for midterm exam questions. Okay, sounds good. Okay, so back to chirality. So when we're talking about chirality, we're talking about the handfulness of molecules. So what is handfulness? If you look at your left and right hand, you can like put them together as mirror image, right? Imagine you have a mirror in between, and they're mirror image to each other. But you can never superimpose your left hand on your right hand. So that's where the concept handfulness come from. So in chemistry, we want to give it or in science, we want to give it a more careful definition. So when we say a molecule is chiral, we're saying the two molecules are not superimposable on its mirror image. So what does that mean? So let's imagine we have these two molecules. They're mirror image to each other. You can easily imagine we add a mirror in between, and that's what they are, right? They're mirror image to each other. If you have your molecular kit, also build a chiral molecule yourself to try it out. And thinking about a definition of the chiral molecule, meaning these two molecules are not going to be able to superimpose on each other. So let's try it. If I put my red one on top of red one, I can never make the blue one to be next to my blue one. No matter how I rotate it, I can never make sure like they are superimposing on each other. One of them is bound to be different. So that's what we call this molecule to be a chiral molecule. all right? And what if I replace one of my red atom with like a white atom? Right. And now you can still organize these molecules so that they are mirror image to each other. But at the same time, I can also just rotate my molecules so that they're superimposing to each other. So these two molecules are no longer chiral molecules, they are achiral. All right, or achiral basically means lack of chirality. And when we look at an achiral object, it will have at least one element of symmetry. So the concept of symmetry is a little bit deeper than what I showed, but basically it's like when you're thinking about your molecule, do we have a plane of symmetry, meaning like you have an internal mirror plane that you can draw? Like in this one. You can imagine we're drawing an internal mirror plane, meaning like if I insert a mirror right in the middle of this molecule, then this part, the top part and the bottom part of my molecule are already mirror image to each other. So this internal mirror plane is making this molecule achiral. All right. What about the cyclohexene example that we did? This is another molecule. Like if we draw it out, it looks like. Okay. So if we draw it out, we have our chair shape. We have a. Right. So if we draw it out, we'll see like there exists an internal mirror image, like right in the middle. So this molecule itself is an achiral molecule. We have an internal plane of symmetry. All right. What about this one? I'm replacing one of the hydrogen with, like, say, an oxygen. Now this molecule will become a chiral molecule. You no longer have that internal plane of symmetry. All right. So first of all, we went over definition of chirality. The chiral itself means handfulness, meaning that the two molecules, they do not have an internal plane of symmetry, and they are mirror image to each other. Let's say that's chiral molecule. And whenever you have a achiral object, basically you're saying this molecule have an internal plane of symmetry. That internal plane of symmetry is making that molecule achiral. And on top of the internal plane of symmetry, which is like a mirror plane, you can also have a center of symmetry. So in this case, the center of symmetry means like if I'm exchanging the position of my CH3 with CH3, chlorine with chlorine, and that's also an internal element of symmetry. All right. And we just went over this example here. It's if you have two molecules in which you can have a mirror plane in between these two molecules, these pairs are a pair of chiral molecules. And now we have these pair of chiral molecules. Let's clear out some of the terminologies in organic chemistry. So far, we went over several terms. We went over constitutional isomers, meaning that these are isomers with a different connectivity. So an example being, well, this, we have 4 carbons, and this one, we also have 4 carbons. Their connectivity is different. So these two are called constitutional isomers. And when we're talking about stereoisomers, we're saying these isomers have the same connectivity. So if we look at this pair, on the left carbon, on one of the carbon, it's attached to 1 hydrogen, 1 red one, and 1 blue one. This one also, one attached to a hydrogen, a red one, and a blue atom, right? The other one being a methyl group. So the stereoisomers will have Same connectivity, but different orientation in space. So if we look at some example here, let's think about these pairs. Let's say this one. We have it wedged out versus, let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So in both cases, they have 7 carbons, all alkenes. Are they constitutional isomers or stereoisomers? Constitutional isomers, because the connectivity is different. All right, and what about this pair? We have it wedged out versus dashed. So their connectivity are the same, and these are stereoisomers. All right. And when we're looking at organic molecules, we'll always refer to things like stereocenter or chiral center. So these are two concepts that are closely related to each other, but not exactly the same. So when we're referring to stereocenter, we're saying atoms in a molecule for which exchanging two groups will create a different stereoisomer. And then when we say a chiral center, we're saying a tetrahedral atom, typically a carbon atom, that has 4 different substitutions. So all chiral centers are stereocenters, but some of the stereocenters are not chiral centers. Let's look at an example together. So let's think about these 2 examples. First of all, let's look at a carbon center attached to like chlorine, CH3, a wedged fluorine, and then a dashed hydrogen versus a carbon attached to hydrogen, chlorine, fluorine, and wedged chlorine. So if we look at these 2 pairs and focusing on the carbon center here, now my carbon center in this pair is both a stereocenter and a chiral center. If we look at the chiral center definition, we're saying tetrahedral atom that has 4 different substitutions. We have 1, 2, 3, 4, right? So we're happy they're chiral center. And they're stereocenter because we're exchanging the position of my hydrogen and chlorine in order to make that pair back to what we have. All right, so my carbon center here is both stereocenter and a chiral center. We can also have an example that a carbon or an atom is a stereocenter but not a chiral center. So let's imagine we have a carbon-carbon double bond, like a trans 2-butene. All right, and at the same time, we can also have cis butene. All right, so by switching the position of my hydrogen and methyl group on one of the carbon, we're changing it from a trans isomer to a cis isomer. So that means my carbon center here, they are stereocenter, but they're not chiral center. Because they're not sp3 carbon, they're not tetrahedral carbon with 4 different things on them. Right. So this part is like the purpose of this entire part is to clear out some of the terminologies. We start by looking at the constitutional isomer versus stereoisomer, and then also we have stereocenter versus chiral center. Another pair that we want to talk about is enantiomer versus diastereomer. So enantiomers, yes.
My question for the past slide, for trans and cis, I guess weighing CH3 and C3CP very differently?
So the question is my CH3 and hydrogen are?
No, like shouldn't the cis one be
Oh, you mean this one? H3C and C, they're the same. It's just like conventionally, I write it as H3C whenever, because I want to make sure the carbon is attached to carbon, not like carbon attached to CH3. It's conventional, it's not right or wrong. You can also write it as like CH3. That's not wrong, it just, I like to write it as H33. Okay, and the next concept we have are enantiomer and diastereomer. So this pair, I'll go a little bit slowly. And if you have a molecular kit, feel free to play around with it and plug things on and off. So this pair comes when you have more than one stereo center. Okay, so when you have like more than one stereo center. When we're talking about enantiomers, we're saying the stereoisomers that are non-superimposable mirror images. So let me just build one for you. Okay. 1 second. I'm just replacing one of my hydrogen on the methyl with a green fluorine and with a ethyl group. So if you have your own molecular kit, you can also play with it later on. And okay, here we go. So we start by looking at enantiomers. So enantiomers are saying these are stereoisomers that are non-superimposable mirror images. So enantiomers, you have these two are mirror images to each other. So like the two molecules we built right here. So let's say I have carbon attached to carbon. I'm looking at my left molecule here. The red one is pointing towards you. Actually, let me make it staggered. So the red one is pointing towards you. I just put red for R for red. The hydrogen is coming out. So something like this. And we have a blue one away from you. And on the other carbon, you have the white one, or the hydrogen, coming out at you. And then you have a ethyl group. And then you have a green one away from you. So that's my left drawing. All right. And what about the right drawing? I'm just rotating, so they're like right mirror image to each other. So we have, on the right-hand side, we have carbon, and the red one coming out at me, the blue one pointing away from me, and then the hydrogen is in the same plane with my carbon-carbon bond. And on the other end, we have the hydrogen coming out. We have the green one on the bottom. And then we have a ethyl group away from each other. I mean, on the same plane. Right. So clearly, these two are mirror image to each other. And thus we say these two are enantiomers. To each other. Let me put it on the same line. And we can draw a mirror image in between. All right, so enantiomers, these are saying the stereoisomers are non-superimposable mirror image to each other. What about diastereomers? So diastereomers are stereoisomers that are not mirror image to each other. So stereoisomers, meaning we have same connectivity, but different orientation in space. But when you have more than one stereocenter, they can be stereoisomers, yet not mirror image to each other, making them diastereomers. So what does that mean? I'm gonna keep my left molecule unchanged, and let's say I just manually switch the position of my green group and then my SO group. So it will become this kind of conformation. So let's draw it on paper. What does that look like? So I'm drawing this molecule here, the molecule on the right. So we have a carbon, and then to the hydrogen. And on the bottom, we have a red one pointing out, a blue one dashed in, and another carbon with a hydrogen pointing out, and my CH2, CH3, and then the green one going in. So these two, they're not mirror image to each other, because if you do a mirror invert, like we do it this way, and you do a mirror invert, let's see. The green one and the white one, they're different position with each other. Okay, let me actually draw it differently. Let me draw it in this specific conformation. So I'm just redraw it so that it's clearer. We have a blue one, the red one, and then the hydrogen. Sorry. And then on the carbon, we have a methyl group. And then the green one pointing out. And the hydrogen dashed in. Right. So in this case, it now becomes more obvious, like between these two drawings, do they have the same connectivity? Yes, right. So on the right carbon, it's always attached to a red one, a blue one, and a hydrogen. On the left one, it's always a green one, a hydrogen, and SO group. But at the same time, they are not mirror image with each other. Because if you draw a mirror plane in between, you see that the green one is facing a hydrogen, and this one, the green one, is facing a hydrogen. So they're not mirror image with each other. Again, if you have your molecular kit, please build it yourself. Yes?
Wait, which of the two images in the top are you comparing it to?
So the top one are mirror image to each other. And then what I did is I took one of my model out. I switched the position of the green one and the SO one. That becomes a diastereomer.
Which one did you not change? Like on
The red one, the red, blue, and white, these I didn't change. I just switched the position of these two groups. Yes?
Are all stereoisomers either an enantiomer or a diastereomer?
I would say yes for this class. All stereoisomers are either enantiomer or diastereomer. We'll also talk about meso complex, which is achiral in itself. So right now, I would say yes for this class. There are exceptions, but as far as we care in this class, we can say yes. And these two are diastereomers. All right. And what if I start from this one on the bottom, and now I change my top molecule, I change their position in space to build an enantiomer. How should I do that? So I want to keep this one unchanged. I want to be able to build a mirror image of the one on the bottom, of the one here. So how should I do that? Let me think. Well, we have a mirror plane here. I want to switch the position of my hydrogen and fluorine. So you see, I have to manually change its spatial connectivity. Okay, here we go. And now these are enantiomers to each other again. So this is the one I built originally. I put it on the left. And this is the one on the right. And now they are mirror image to each other again. All right, and we can draw out that enantiomer again. So on the left, what do we have? We have carbon. Let me see. I'm gonna put my hydrogen to the position. I'm just organizing the atoms so that they're the same orientation in space. Okay. So I draw my hydrogen out, the red one wedged out, my blue one dashed in. And on the right-hand side, I'm making a carbon bond with the green one wedged out. And then the hydrogen dashed in. And then you have I think I'm missing. And your acyl group coming out. Right, so these are now enantiomer to each other. And let me name them A, B, C, and D. Now the question becomes, what's the relationship between your molecule B and D? They're not mirror image to each other. They are stereoisomers. They have the same connectivity, right? So they are distereomers. Yes.
This might be a little bit hard to phrase, but could you basically say that diastereomers, like, I guess they wouldn't both sides be flipped around, like one of the, for example, the B and R's are switched, but everything else is a mirror image, so I guess you can just look for a group that when you flip it around would be mismatched, and that therefore...
The other way to put it is diastereomers are stereoisomers that are not mirror image to each other, or stereoisomers that are not enantiomers. Or in this case, when we're looking at relationship, what is the relationship between we have two more pairs of diastereomers between your A, B, C, and D. What are these two pairs that are diastereomers but not enantiomers? We have, what about relationship between A and D? So these are also diastereomers. And also between your B and C. These are also diastereomers. All right. Again, if you have your molecular kit, build the 4 molecules and see how come they're not mirror image to each other. And some of the example question I might ask you to do is, can you draw all stereoisomers of this molecule, which is an epoxy with a bromine and chlorine? So first thing you want to do is to identify what are the chiral centers we have in mind, right? So in this case, we have 2 chiral centers. One is this carbon. We also have a hydrogen that we didn't draw. And here is another carbon. So for each of these carbon, we have 4 different groups attached to that carbon. Consequently, we have 4 different stereoisomers because we're looking at a molecule with 2 stereo centers. So what are the molecules we can draw? So think about this. We can start by putting it as like bromine comes out, hydrogen dashed, chlorine wedged out, hydrogen dashed. Or your hydrogen are cis to each other in this join. Alternatively, if you're doing a mirror flip of the molecule, you can get a join where your hydrogen is wedged out, your bromine is dashed, and your chlorine is dashed with your hydrogen being wedged out. So these two will be your enantiomers. And in both cases, these two are cis to each other, or the hydrogen are cis. Yes?
Are chiral centers only going to be like carbon center atoms or can be?
So chiral centers, by definition, let's go back, right? Chiral center is tetrahedral atom, typically carbon. You can have other tetrahedral atoms when you go down the periodic table. That has 4 different substitutions on them. And coming back here, we can draw diastereomers by only changing one of the carbon center. And that becomes, well, let's keep my bromine unchanged, hydrogen, and then put my hydrogen here. And putting my hydrogen on wedge, and chlorine on dash. And these will be my diastereomers. Yes?
Wait, so for the top one, if you change the left to the hydrogen just being a wedge and the chlorine just being a dash?
Well, that's the last one we're drawing. Right, so this one, we're drawing it as hydrogen, and your, my bromine. Okay, so I'm changing the position of my bromine and my hydrogen, and the rest kept the same. And these pairs are also diastereomers, enantiomers. And then these are diastereomers. These are also diastereomers. All right. So this section, we're elucidating some of the concepts. We're talking about constitutional isomers, stereoisomers, chiral center, stereocenter, enantiomer versus diastereomer. Yes,
So if you're asking for all the stereoisomers, you would do it for all stereoisomers?
correct. So there's going to be a combination of a bunch of stereoisomers. Yes.
So there could only be 4 total?
Well, for 2 stereoisomers, yes. But when your molecule gets bigger, the number of stereoisomers becomes way more larger. So that's why chemistry is so complicated, because the more stereocenter you get, the more stereoisomer you can involve. Okay, so now we have an idea about the relative relationship between my stereoisomers. Now it's time to give my stereoisomer an actual name. So that comes to the assignment of our absolute stereo configuration, or the RS naming system of a chiral center. So I'm going to go pretty slowly here with you. So basically, we're going to go over the rules, and then we'll do several examples together to see how do we apply these rules to assign absolute stereo configuration of a chiral center. Right. So let's get started. So when looking at the connectivity of an atomic number, what we're saying is that the higher the atomic number, the higher the priority. So what does it mean? Let's look at here. I'm just going to give the number, the red and blue one, a little bit more name. So the red one will be my oxygen. So like a OH group. The green one is my fluorine, and fluorine is number 9 oxygen is number 8. And then the blue one, let's set it to be my NH2, or nitrogen. And that's number 7. And carbon, obviously, is number 6. So, looking at my molecule here, what do we have? If we're looking at this specific chiral center and assigning the priority, red one is my oxygen, being 8. Blue one is my nitrogen, being 7. Black one is my carbon, being 6. White one is my hydrogen, being 1. So which one has the highest priority? So that's the red one, right? So the highest priority, second highest, third highest, and lowest priority being my white hydrogen. All right, that's for this terminal carbon. What about the middle one? The middle one becomes more complicated. Now we look at the middle one. We have fluorine, so that one is for sure our highest priority. And then we start to count my second 2 carbons. Now both of them are carbon, so that goes to rule number 2, which is if the priority cannot be assigned per the atom to the chiral center, so in both cases they're carbon attached to the chiral center, we look at the next set of atoms. So the priority will be different at the first point of difference. So if we look at these 2 carbons that are both attached to the center carbon, this one has 2 hydrogens attached to it. This one has 2 hydrogen and 1 carbon, right? So this one has carbon, oxygen, nitrogen, and hydrogen. So my oxygen obviously have a higher priority than the carbon attached to it. So this one being the second higher priority when we're looking at this chiral center here. Because oxygen has higher priority, higher atomic number than carbon. All right. And next up, if we have a double bond, basically, like in here, if we have a double bond, we're counting that carbon twice. So that's the rule of priority. You first look at the atom directly attached to the chiral center. If they are the same, you go one more atom until you find a difference. All right, so that's a priority rule. Secondly, we can then look at the procedure to assign the absolute stereo configuration. So once we identify a chiral center, again, a chiral center is a tetrahedral center, typically carbon, identifies 4 substitutions, assigns priority from 1 to 4 for each substitution. That's what we did, right? So here we have 1, 2, 3, 4, 1, 2, 3, 4. That's what we did so far. And orient the molecule so that the group of the lowest priority is directed away from you. So for example, in this case, if we're looking at this one, and I want to rotate my molecule so that my hydrogen is dashed. All right. So if we look at this plane, construct by my nitrogen, carbon, 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 my oxygen is wedged out, my hydrogen is dashed in. And then you can read the groups projecting towards you in the order from high to low priority. And if the group reads clockwise, it's R. If they're counterclockwise, it's S. So let's use this one as an example. We look at this one. We draw it on the board. So I'm drawing my carbon. And then we have a wedge one coming out. Let's say that's my nitrogen. And my red one, my oxygen. And my hydrogen is dashed in. And on the left, we have my carbon. So what we get? And then we number it, right? We have And if we look at my center carbon, again, in my center carbon, I want to organize it so that my hydrogen is pointing away from it. So in this orientation, I want it to be super away from me. And in this orientation, what do we have? Now we have a carbon, and then my hydrogen is away from me. Oh. And then this group is coming out, wedged out. And that's my CO. NH. And then you have the fluorine, and then the other methyl group defining the plane. And we can assign the numbering. So fluorine is my 1, 2, 3. And this one is coming clockwise, so it is R. All right, yes.
What if our number one, like say an example, what if we're forced to have our number one be wedged on the whiteboard?
Okay,
Is
that
there
one.
any examples where our white number one, like when we begin the count, is it ever gonna be dashed?
Okay, so here's the thing. When you're looking at the molecule, there is no such thing of correct drawing. It doesn't matter which one I put in the wedge. It's more like if I'm rotating this bond. Remember, we have free rotation over the single bond. So you have free rotation, right? So when assigning the R and the S absolute stereo configuration, you want to rotate your molecule in your mind so that my lowest priority group is on the dash. All right. And in that case, it basically means like if you have your molecular kit with you, okay, great, you can rotate and look at it. Or if you have very good 3D imagination, you can imagine the molecule rotating in your head, that also works. I don't know which one works best for you. So in this case, there are different drawings we can do on top of the one I did on the board. So for example, I can put it this way so that my carbon, and then we have hydrogen that's dashed, and I can put my NH2. My nitrogen is wedged out, my oxygen is like normal, and then the other one being a carbon, and then you have H attached to a SO group. Right, so if we're joined like this, it's the same idea. You can put 1, 2, 3, and it's still counterclockwise. All right. How are we feeling so far? Let's do one more example together. Let's say this molecule. Again, this one is actually more straightforward than what we did. So I'm still gonna do fluorine as green. And let's say my bromine is red, my chlorine is blue. And down here, let's see, this one right, okay. So these two. My fluorine is back. Okay, it doesn't matter how I put it. Nevertheless, so let's just assigning the absolute stereo configuration here. So in this one, we look at the drawing we have on the board right now. So let's say my, my bromo is blue, and then my chloro is red. Okay. So starting from this drawing, which is the hydrogen is like normal line, your bromine is normal line, the chlorine wedge out, the fluorine dash in. we can assign the priority, right? So my bromine is definitely higher than chlorine, than fluorine, than hydrogen. But now my hydrogen is not on the wedge nor on the dash, so we need to reorganize our view of this molecule. So that's saying we can redraw this molecule so that my hydrogen is dashed. Right, so if I define my plane as carbon, and then you have a chlorine on the top, and then a bromine, unchanged. And then you have here your green one, which is your fluorine wedged out. And then your hydrogen dashed in. And then you can put in, again, 1, 2, 3, and you have a R configuration. So far, so good? You can also like do a different drawing. Like what if I just wanna put my bromine on, let's see. What if I rotated my molecule so that I have my carbon in the middle, and then I put my bromine on top, and my chlorine on here, and then my fluorine wedged out, and then my hydrogen dashed in. Right, so that's a different way of looking at it. We have 1, 2, 3. We still have an R. So this is why we call it an absolute stereo configuration. As long as you have an R configuration, you can draw your molecule however you like by rotating it to different positions. Like all 3 of them are equivalent to each other, just the same molecule, different drawing. And in all 3 of them, we'll be able to derive a R stereo configuration. Yes?
So you're saying is without even like envisioning it or using a molecular kit, we can literally just assign the lowest priority molecule, dash, and then do whatever we want with the others. It doesn't matter.
Yeah, I mean, if you can imagine in your head manually rotating it from like this configuration to this configuration to this configuration, I don't care how you get to the answer.
But do we even have to imagine it? Can we just literally assign?
You can use your molecular kit in our exams or so. Like once you get familiar with it, you don't need one. But when you first get started, I still highly recommend you get a molecular kit or some kind of visualization tools so you can look at the chiral center and start rotating the molecule in your mind. Yes?
My question is, even though they're all in the same group, how did you determine that bromine had first priority?
Okay, so that goes to the priority rule. So that's this entire slide. So priority, first of all, you look at the atomic number. Secondly, if both of them are carbon, then you look at the next atom attached to it. All right. And, well, in this one, we'll end here to be like assigning your R and S stereo configuration. Like use this one as a final example, right? We can assign my chlorine to be 1, my ethyl group to be 2, my methyl group to be 3, and my hydrogen on the back, so this becomes a S stereo configuration. So, absolute stereo configuration, practice, practice, practice. We'll pick up from where we left over today on our next lecture.